Hello again from a very hot Los Angeles, California. I am Marin Steiner again, and for today's interactive advanced concept presentation 7, we're going to do some balloon geometry. The goal today is to explain the different electron domain geometries as best as possible using balloons as the model. Each balloon will represent an electron domain, either a bonding pair or a lone pair of electrons surrounding a central atom. When we connect them together, we're going to simulate the adoption of the lowest energy arrangement predicted by the VSEPR model. So for today's experiment, really our only materials, it's pretty simple. We just have a bunch of balloons. So here we go. So first, let's start off by doing a model for linear geometry, and we'll use 2 electron domains for this one. So step 1, we'll take one balloon here. We will inflate it. Sorry for, we'll do this a little off camera here. So we'll tie this one off. Hopefully I don't mess this up while I'm trying to film. That's kind of embarrassing. Oh goodness. There we go. Okay, so we've got one balloon. We're going to do a second balloon because we're using 2 electron domains here. Oh, that didn't work. Let's try another one. It's so hard to tie. Oh goodness. This is happening because I'm trying to film. There we go. Okay, so now we have our second balloon there. So we're going to connect these 2 set of balloons by twisting the points, which is right here, if you could see that, on the connection. And here, basically, we will do this, and this will give us our, sorry about that. This will give us our trigonal bipyramid, I'm sorry, move that back up. So this gives us our trigonal, or linear geometry with 2 electron domains right here. So a 2 electron domain structure produces a linear molecule with electron groups that are basically 180 degrees apart. In chemistry, the linear molecular geometry describes the geometry around a central atom bonded to 2 other atoms placed at a bond angle of 180 degrees. Linear organic molecules such as acetylene are often described by invoking a sp orbital hybridization for their carbon centers. An example would be CO2 or like xenon. That's an example of that. So next, let's try to do a trigonal planar geometry with 3 electron domains. So step 1, we already have our 2 balloons, so we're going to use that right here. But we're going to need a 3rd balloon for this one. So let's try and do this again. Okay, try and tie this off now. There we go. Got that one a little bit easier this time. Okay, so now we have our 3 balloons. So basically what's going to happen is we're going to tie them off, and they're going to come at the angle like this, if we can see here. And then we'll tie them off right here. So there we go. You should be able to see that. So trigonal planar geometry is a form of molecular geometry model with 1 atom at the center and 3 atoms in the corners of an equilateral triangle called peripheral atoms, all in one plane. So trigonal planar is basically a molecular geometry model with 1 atom at the center and 3 atoms at the corners of an equilateral triangle called peripheral atoms. And it forms bond angles at about 120 degrees. So next, let's go to tetrahedral geometry, which has 4 electron domains. So we'll take our 3 balloons that we've had previously, and then we're going to get a 4th one here. Oh goodness, tying these off are just very difficult. Alright, well, I'm going to hold it because this one doesn't want to tie. Okay, so here's our balloon, and then we're going to have our other balloons here. And basically what this is going to look like is this. You should be able to see that on camera. So that is a tetrahedral molecular geometry, which is a central atom located at the center with 4 constituents that are located at the corners of the tetrahedron, and the bond angle is approximately 109.5 degrees. So we'll let these ones go there. In summary, molecular geometry isn't the easiest thing to grasp, as it definitely hasn't been. It's also not obviously the easiest to tie off these balloons for me. But 2-dimensional representations of molecular geometries predicted by the valence shell electron pair can be difficult to grasp. So 3-dimensional models like we did today, however, would give us the opportunity to view and manipulate models as needed and ideally make molecular geometry easier to understand. So today we represented electron domain, either a bonding pair or a lone pair of electrons, and we surrounded that with a central atom. And when we connected the balloons together, we adopted the lowest energy arrangement predicted by the VS-EPR model. So hope you enjoyed this, and hope everyone has a safe and wonderful weekend. Bye for now.